Good morning. As application for inverse problem, we present here parameter and temperature estimation using photoacoustic technique. The temperature is important. Knowing temperature distribution inside or in vivo is very important because diagnosis of diseases such as inflammation, infection, or tumors, or thermal monitoring such as laser ablation surgery or local hyperthermia. Then, therefore, the necessity of a non-invasive temperature measurement in vivo make us this idea, gives us this idea to use inverse problem to estimation of temperature. The inverse problem needs some observation. The techniques for non-invasive observation can be microwave radiometry, magnetic resonance imaging, ultrasound, and photoacoustic technique. This technique suffer from some defects, like microwave radiometry has relatively poor temporal and spatial resolution of measurement and susceptibility to interference from other electrical signals. MRI has high cost, unreliability in fat, and susceptibility to artifact induced by organ displacement. And ultrasound has low sensitivity of physical parameter with change of temperature. Then we used photoacoustic to get our observation. In this work, objective was evaluation of photoacoustic inverse problem through Markov Monte Carlo method as a Bayesian inverse technique for estimation of thermophysical property, and temperature estimation of tissue throughout the estimated parameters. The physical problem in this work is described by three equations of momentum conservation, mass conservation, and pressure density relation. By combining these three equations, we get second order equation of photoacoustic. Indeed, photoacoustic happen in under conditional thermal confinement. Thermal confinement means the pulse duration is very less than thermal relaxation time. This gives us adiabatic heat transfer. In adiabatic heat transfer, with temperature rise, pressure rises too. We did this case for two cases. In the first case, we did for one-dimensional case, and after that, we did it for we developed it to two-dimensional case. In one-dimensional case, we assumed the heat equation, the product of absorption coefficient and fluence rate of laser, which is described here in one-dimensional case by Beer-Lambert law. And in two-dimensional case, the fluence rate was described by delta P1 approximation of fluence rate. Then in second case, which was a two-dimensional case, we considered the problem as an initial value problem, which the initial pressure was product of absorption coefficient, time Grunessen parameter, and fluence rate. And Grunessen parameter here is our parameter which is vary with temperature significantly and is product of second square Sandeswit and second Sandeswit square time thermal expansion coefficient over heat capacity. In one-dimensional case, we assumed a layer of muscle with thickness of 5 millimeter, duration of 10 microseconds. Here we can see this numerical analytical solution of one-dimensional case. And here is presented the result of amplitude of photoacoustic wave is increasing with temperature. And this increasing is linearly. In one-dimensional case, we did analysis of sensitivity or coefficient to know which thermal physical parameter are sensitive for estimation. Sound speed and thermal expansion coefficient has a good sensitivity to estimation in this model, but thermal expansion coefficient has a correlation with laser energy density and specific heat. Then we assume them as a one parameter named F. In this work, we used inverse problem through Bayesian framework. And Bayesian framework indeed a probability density of posteriori. Here is probability density a priori, which is information about parameters before measurement, and likelihood function, which is measurement error model, and probability density of the measurement. As depending on the probability density a priori assumed for the parameter, the posterior distribution may not allow an analytical treatment. Then here we used posterior distribution is explored by using the Metropolis-Hastings algorithm of microwave chain, Markov chain Monte Carlo method. To generate some measurement, we used our exact result by adding a Gaussian error with zero mean and a standard deviation of 0.2. Here we can see the sound speed is estimated by a Markov chain states with error less than 1% of exact value in 3 different temperatures. And here is marginal posterior histogram of sound speed. For other parameter F, we could get the result with Markov chain state 2 with an error of less than 1%. Here we can see marginal posterior histogram of parameter F2. It has a Gaussian distribution. And for other case, we did for different temperature for get a correlation between the parameter and temperature. This is for parameter F. And finally, we get a relation between the parameter we could estimate and the temperature. We can see this has a linear trend. In second case, which was a two-dimensional case, we assumed a hyperthermia thermal treatment. Indeed, we have a muscle contain a tumor region injected by nanoparticle of gold, irradiated by a laser, duration of 40 seconds. After 40 seconds, we use photoacoustic technique to estimate the temperature distribution in tumor region. Here we can see initial temperature distribution in the tumor region, in the muscle region. Indeed, here in the tumor region, because higher metabolism, the temperature is 1 degree higher than other part. Here we can see the temperature distribution after 40-second irradiation of laser, indeed after hyperthermia. Here we have the solution of optical model by delta P1 approximation, and this is a fluence rate distribution of the laser. By the fluence rate of the laser is generated initial pressure, and we can see the pressure rises about 2 times 10 to the power of 4. We used 4 transducer or sensor in bottom surface and other 5 in top surface. We get indeed, we assumed we have the sensor in the surface of the model to get our photoacoustic wave. We used this. We used the solution of exact problem to generate some measurement, numerical measurement, with adding Gaussian error with 0 mean and standard deviation of 5% relation to exact pressure in all sensors. Indeed, in some volume, we mark them with numbers to specify their Markov chain states. For estimation of Grunessen parameter in 2-dimensional case, which is temperature dependent, we used 2 type of prior information. We used total variation and Gaussian Markov Random Field. Here we can see the result for volume in the 2-dimensional case. In the tumor region, we can see the result for the case of Gaussian Markov Random Field is very better than other case, which is total variation. In other case, we can see the Markov state, the Markov chain state, and the marginal and posterior marginal posterior histogram of the volume. By the Mino Markov chain states, after their convergence, we get a distribution map for Gaussian for Grunessen parameter, and by the relation between temperature and Gaussian and the Grunessen parameter, we could estimate the temperature map inside the muscle and tumor region. Here we can see for here is a histogram of local temperature obtained with Markov chain for the Grunessen parameter. For the volume was specified by the number. And at the last, the obtained result showed this case, which deals with the smooth gradient of temperature. Gaussian Markov Random Field is a more proper as a prior information. And the Grunessen parameter related to pixels, which are inside the radiation domain of the laser pulse, and with better fluence rate can be estimated with accuracy less than 2%. And the results show the MCMC method is sensitive to temperature difference and can estimate a temperature-dependent parameter, such as Grunessen parameter at different temperature. And the idea showed that photoacoustic can be used to map temperature or temperature distribution with accuracy less than ±1 degrees centigrade, which is sufficient for tracking the essential isotherm in the case of clinical procedure. Thank you very much.
Thank you. Questions?